Everyone. So we have two presenters today. And first up, we have Rosemary Killen, who is going to be talking to us today about some ground-based observations of the lunar sodium exosphere. So Rosemary, whenever you're ready, and everyone who is not talking, please put yourself on mute. And so, Rosemary, since it's half an hour, do you want us to interrupt you with questions, or would you prefer if we waited until you're done presenting?
If something is not clear, please interrupt. Otherwise, I'll take questions at the end. Okay?
Okay, sounds good. And I see a few more people dialed in. So we now have John, Keller, Cynthia, Elizabeth, and someone else dialed in, but I'm having trouble locating. But anyway, all right. So Rosemary, yep, go ahead whenever you're ready.
Okay, I'm Rosemary Killen. I'm at Goddard Space Flight Center, and I have a number of co-authors. I decided to show a little bit of background because I don't know how many of you are aware of what we've done. We have designed and built a lunar coronagraph, and it's out at the Weiner Observatory in Sonoyta, Arizona, which, as you can see, is the backside of nowhere, which is very nice. And it's a very small place. It's just this little structure with a roll-off roof. And so that was just a picture of it with the roof rolled off. And I'll show you, this is what our coronagraph looks like with the covers removed so that you can see the telescope. This is Roy Tucker, who is our technician. He actually worked at the University of Arizona. He's now retired. And he was in their optics lab for many, many years. So this is a small telescope, and the back end is a coronagraph, which means that we have an occulting disk which we can move on and off so that we can occult the moon and just have an image of the sodium corona. And we have on-band and off-band filters. These are narrow-band filters, 1.5 angstroms wide, so that we can just look at the sodium D line. Of course, we have a CCD cooled to -40 C. We have calibrated the filters. And of course, we have the sodium lamp to calibrate. So we take an image on band, off band, and we take images with the occulting disk on and off. And this is what our screen looks like because we have lots of applications. We run the telescope with off-the-shelf software. It's called SkyX. It's commonly used by just any amateur, but it runs the telescope for us quite well. All of this is remotely operated. We can operate remotely from my office at Goddard or from home, which we've started to do. Of course, since we're not at Goddard, we can run from home. We have, the first thing we discovered when we started this project is that we need a really, really good auto guider. So you can see the guide scope image on the upper left. We take an image of the moon, and then the auto guider is actually guiding on a bright crater, which you can see on the upper middle. We guide on a spot on the moon. And then on the right, that is the image from the science camera. And we have, you know, the software to move the occulting disk and the filters on and off. So you're all familiar with the moon and its phases, but what I wanted to point out is that what we're looking at is the corona at the terminator, and where we're looking is obviously a function of the time of the local time on the moon. And so we can get the whole corona, north, south. I haven't reduced the night side, but we do have the corona all the way around. But of course, what we're looking at is a particular time of day. So we don't get all of the local times at once, but we do have local time as a function of the lunar phase. And this is an example of the raw observations. And because we're guiding on a spot on the moon is fixed with respect to the occulting disk, so we can move the occulting disk on and off, and the moon is exactly positioned at the same place so that we know exactly where the limb of the moon is and where the occulting disk is. And so we know how far away from the surface of the moon we're measuring. And one thing that we quickly realized is that it was really difficult to get the scale height all the way around the moon with just the image that we have. So we started doing the polar transform of the image so that we can just take scans horizontally with height on an image like the one on the right, and get the scale height all the way around the moon. And this is what a limb profile looks like. The altitude beyond about 4,000 kilometers is just noise. So we fit the line profile on a log scale. It's a straight line, so we get the scale height then. And this is what, I mean, it's kind of messy. So this is what the scale heights look like for 2018 data. But one thing you notice is the scale heights are not constant. But on average, I mean, these are scale heights from the waning phases in 2018, and they average about 1,000 kilometers. And what that means is that's about 4,500 Kelvin. So what we're looking at is obviously the corona above about 150 kilometers. So this is the part of the corona that is hot. And on average, it's about 4,500 Kelvin. And what we're probably observing is the tail of a non-Maxwellian distribution. So, 4,500 Kelvin is on the high side of what's expected for impact vaporization. So we might be looking at impact vaporization plus impact sputtering. And I'll show some evidence that we also have radiation pressure effects. And that was actually predicted by Smith and Marconi. They wrote a really nice paper in 1995. So the data here, the asterisks are cosine functions fit to the equator. And the main point is that what we have is column abundance that's pretty flat. And the reason is because the scale height increases with latitude. The other thing we've noticed is that the column abundances are largest both at dawn and dusk, and minimum at noon. And I think that was extremely unexpected. So this is just raw data, and I haven't fit it to a function, but you can see versus local time, the column abundance, it might minimized somewhere between 11 and noon, but and then it's it's kind of messy. It's not nice function, but there's clear evidence that that maybe this is a radiation pressure effect, bearing in mind that we're looking at the high temperature portion of this corona. The other thing that we noticed is that the 3 highest column abundances recorded were consistent with high ion fluxes, and we confirmed that with Artemis data. These were afternoon events inside the magnetosheath. So I think we have really good evidence that sputtering is playing a part in producing the corona, especially when the moon goes into the magnetosheath. We had shown years ago that the corona increases just before the moon comes out of the magnetotail. But what is happening there, it's because the moon is in the magnetosheath, and that happens both when it goes in and when it comes out of it's not happening in the magnetotail, it's happening in the magnetosheath. And this is just an example of the Artemis data that one of the data sets that confirms that when you have this increase in the flux of ions onto the moon by a couple orders of magnitude, and you really see that dramatically affect the corona. Now, in comparison with the LADEE data, I just wanted to point out that the LADEE data reduction assumed that there was a constant temperature and that temperature was 1200 Kelvin. But what we're showing is, at least for the high altitude corona, that the temperature is much higher than 1200 Kelvin, and it's not constant. So our key points are the lunar exosphere is enhanced during periods of enhanced ion flux to the surface. The scale heights increase as the moon approaches full phase. And it really increases when the moon is in the magnetosheath. Column abundances are least at noon and increase at both terminators. I don't know if this is significant, but the waning phases showed more deviation from trends than the waxing phases. I have no idea why. And just to point out that our data are all from about 150 kilometers above the surface to 1 lunar radius from the surface. And so these are our main conclusions. And this is our team out there at the Weiner: Tom Morgan, Roy Tucker, and myself. Okay, so I'll take questions.
All right, thanks, Rosemary. And go ahead, I think that was Michael.
Yeah, this is Michael Poston. Really cool work. You said the scale height increased with increasing latitude?
Yes.
Was that expected?
Well, actually, it was expected if you go back to the Smith and Marconi paper. And that is because of radiation pressure effects. Of course, this is much more pronounced for Mercury, where the radiation pressure is larger. But it also happens, in his simulations of the lunar exosphere, he shows the same thing. And this isn't necessarily because of the temperature, if you will, of the source, but it's because of acceleration by the radiation pressure.
Okay, and then the other question, or I guess this might be more of a suggestion, could perhaps mineralogy or surface composition lead to some of the asymmetries and other kind of surprises you've seen?
Actually, I saw an enhancement in the southern hemisphere And there was a paper by Chandra who I think it was Chandra results, where they seem to have an area of enhanced sodium in the surface. And I talked to the author, and he indicated that it would be really nice to get more, you know, global coverage of the composition. But with the masks data at Mercury, I don't know if you know, we did get really good correlation for magnesium with the, you know, there's this area on the surface of Mercury where the magnesium concentration is just really enhanced. And we can see that directly in the exosphere. So you know, it ought to track local surface concentrations as it does at Mercury.
This is Carly. I want to follow up on that a little. It's a fascinating aspect of what you're doing. The difference in waxing and waning. If I have my geometry correct in my mind, there's more Mari. I'm thinking in terms of the large expanses of Procolarum in one versus the other. Could that be a source of your difference between the waxing and waning?
Absolutely, we're looking at different surface areas. The limb is, you know, obviously over different different places, and one side has more Mari. You're correct.
Cool.
Okay, so I see Shyama and Elizabeth have their hands up. So Shyama, and then after that, Elizabeth.
Yeah, thank you, Parvati. Just to follow up on that, as you mentioned, like we had some observations with Chandrayaan-1 of detecting sodium in some part of the southern hemisphere. Right now, with the Chandrayaan-2 orbiter, we have had several spots on the lunar surface where we have been seeing sodium lines and still working on it. So we would be really keen to see you know, whether there is any relation with the sodium exosphere observations that's been happening. So that's one thing. And next I had a question was, do you see any difference every month as it enters the geomagnetic tail? You did talk about the magnetosheath, but inside the tail, are there any specific changes in the sodium that you have observed?
Well, it's difficult both because of, because of weather. We don't often get a complete lunation of data. Actually, this month we had an entire week where we had perfectly good sky, but a lot of times we don't have good coverage. And we don't have good coverage in the magnetotail because as we get close to full moon, it's more difficult to observe. I was observing during the last full moon, and the first observation I took was overexposed, so I lowered the integration time, and I think I got some good data, but it isn't always, we don't always get good coverage in the magnetotail. So that's why we're continuing to observe. And the other place where we typically don't get is near new moon, which would be really interesting, but we just can't observe near new moon.
Okay.
So we
Okay,
don't get complete coverage is my answer, but we're still trying to get as much coverage as possible.
Yes, thank you.
Hi, so this is Elizabeth. I am not an expert or that familiar with the lunar radiation environment, and I was just wondering if you could speak a little bit more to what exactly radiation pressure is and how it's affecting the lunar surface.
Okay, well, the sodium atom, it absorbs a photon. It absorbs the sodium wavelength in the solar spectrum, and that gives it momentum anti-sunward. Now, when the sodium atom re-radiates, but it re-radiates more or less isotropically. The D1 is isotropic. The D2 is not quite isotropic, but you can consider that the radiation is re-radiated isotropically, which means even though some of it is re-radiated in the opposite direction, you still get a momentum push anti-sunward, and cumulatively the atom gets accelerated anti-sunward just because of this momentum from the photons.
Okay. So you're saying there would be more radiation pressure at the equator than at the poles?
Well, at the equator, it isn't necessarily at the equator. At the subsolar point, then the atom is pushed towards the surface, and actually what that does is lower the scale height because the atoms are like pushed towards the surface. And so maybe we're seeing a lower scale height at the subsolar point, and there's fewer of the atoms are getting out to where we're looking. So if you're looking like at the exosphere close in, you might see just the opposite, in that there would be more column at the subsolar point for the part of the exosphere that's bound. We saw that at Mercury. We saw the effects of the radiation pressure decreasing the scale height at the subsolar point, and that's just because it's pushing it towards the surface. But if your atom starts out near the terminator, that radiation pressure is going to push you away from the surface.
Interesting.
Yeah.
Awesome. Thank you.
Right, Cesare?
Hi, Rosemary. This is Cesare. Very interesting work. So you mentioned that there is a specific correlation between the Colin density and the ion flux. So I was wondering, can you distinguish how much of this is direct sputtering versus sputtering that enhance the diffusion of the sodium from deep in the regolith, so like ion enhance the diffusion.
Oh, you want to know if it's sputtering or ion enhanced PSD or something?
Yeah, yes, exactly.
Actually, yeah. I think that you would, in order to answer that question, what you need to look at is the scale height, because if it's ion enhanced PSD, there's going to be more PSD, but the temperature is still going to be consistent with PSD.
Okay.
And it would be nice if we could observe the whole exosphere at the same time, in other words, all the way to the surface, to see, because those of you who've followed this for a long time know that the scale heights measured by Potter et al. From Kit Peak with the stellar spectrograph, and they were observing much closer to the surface, and their scale heights were much smaller. And so there probably is at least a two-component exosphere, one which is colder and the one we're looking at, which is hotter. And you might, if you could observe that low the part of the exosphere that's below 150 kilometers to see if you had more sodium with a lower scale height during ion impact, or if it's sputtering, which increases the scale height and increases the column. But we do see an increase in the hot portion, which would indicate that at least part of it is sputtering.
Right, yes, okay. Okay, cool, thanks.
Okay, so we'll take two more questions and then we'll move on to Colin. So one question is, so Ed Patrick asks in the chat window, what are the highest particle densities? Could an in situ measurement, could an in situ instrument measure these? And what about other species like Fe or S?
Oh, I don't know any. I'm going to answer the second question first. Fe, we saw iron in the exosphere at Mercury, and I expect you would see the same thing at the moon. The densities are lower at the moon, so it's a difficult observation even at Mercury. And sulfur is difficult to observe spectroscopically because the emission lines are so far in the UV. We never were able to observe sulfur in the exosphere at Mercury, even though we think there's a fair amount of sulfur on the surface. That would be something that you might be able to do with a mass spectrometer or an ion mass spec. But yeah, it would be an interesting observation. So what was the first question?
So the first part of it was, what are the highest particle densities and could an in situ instrument measure those?
Okay, so the particle density at the surface is pretty small, although the column abundances are between 10 to the 8. And in fact, our highest ones were almost 10 to the 10 for those very few observations. But the actual particle abundances are small, just a few per cc.
Okay, and we'll take one last question from Carl.
Hi, Rosemary, it's Carl Schmidt. I had one question. Have you compared line widths from Donna's measurement with the Fabry-Perot McMath to your scale height temperatures?
We have, and we remarkably well agree. Yeah, and in fact, well, they obviously they can't observe at Kip Peak anymore, and I'm trying to I'm talking to them about, you know, whether they can find another place to house their Fabry-Perot, because it would be really nice to get more of those observations. But they show very large line width, as you probably know.
Thanks.
Okay, well, thanks, Rosemary. That was really interesting, and A+ to everyone for class participation. Our second presentation for today is from Colin Hamill. And so while Colin is setting up his screen, and oh yeah, okay, let's see. So Rosemary stopped sharing. So Colin, and we see your screen and it looks wonderful. All right, so Colin just graduated last week from Towson University, as I found out today that he just graduated last week. So congratulations, Colin. And he will soon be off to do a PhD at Purdue. But before that, he is going to talk to us today about some work that he's been doing at APL on understanding Mercury's polar deposits. So Colin, whenever you're ready, and Would you prefer if we interrupt you in between with questions, or do you want to wait till the end?
Yeah, please interrupt if anybody has questions.
Okay, but I will just say, you know, since we have only half an hour and this is exciting stuff, if it's not pressing, I'm going to suggest people wait until Colin has finished going through his slides. But otherwise, Colin, whenever you're ready, take it away.
Cool, thank you. Yeah, so I've been an intern at the Applied Physics Lab since May of last year, where I primarily research Mercury's cold traps with my mentor, Dr. Nancy Chabot. And I'm super excited to talk to you guys about some new temperature constraints of Mercury's volatile polar deposits. So Earth-based radar data and messenger data show evidence for water ice in Mercury's polar deposits, partly in the form of high reflectance surfaces in Mercury's polar craters. However, most WAC images of messenger's polar craters reveal low reflectance surfaces with sharp boundaries and brightness variations, like this one on the right. This image is located within a small portion of a crater named the Prey and shows the low reflectance surface that is thought to be made up of volatile organic compounds. Understanding the thermal environments of the low reflectance boundaries, like here, is like the boundary of that low reflectance deposit, and understanding the brightness variations within the low reflectance polar deposit is key to understanding these volatile deposits and hasn't been possible with the existing low resolution topography models until now. And this work focuses on two fundamental questions: what are these volatiles and what are their characteristics? So this is a map of Mercury's North Pole, and in red are radar bright regions, which are due to water ice on or just below the surface, and green is the permanently shadowed region in which most radar bright regions are located. Blue shows the area of low altitude images from messenger, like the Prey is up here in the top left, the one we just saw. And these are the digital elevation models that were produced at a resolution 4 times greater than that of the North Polar regional models that were used previously to study Mercury's cold traps. These 6 craters range from 18 kilometer to 47 kilometer diameters, and they're all home to a low reflectance polar deposit. These high resolution elevation models use messenger altimeter data as well as the wide angle camera images in a technique known as shape from shading, which uses images to infer the shape of the craters. And as seen in the leftmost image, the North Polar DEM, the old one of 500 meters per pixel, is too pixelated to resolve brightness variations of the WAC images within the scale of a few hundreds of meters. And as expected, the new model at 125 meters per pixel provides much better resolution. And then on the right-hand side, when you combine the shape from shading in tandem with the MLA data, you have a really pretty model, and it gets rid of the residual streakiness that's a result of the altimeter tracks on Mercury's surface. So now that we have these high resolution elevation models, the solar and thermal environment can be mapped in high resolution as well. So that's a digital elevation model seen before. And this is an average solar illumination model, which simulates the percentage of time that the crater surface is exposed to direct sunlight in a Mercury solar day. So you see almost 50% of Enzer for this one is permanently shadowed, absolutely no direct sunlight. And then, you know, creeps up more 10 to 20% sunlight. And then on the very ridge, like the rims, it's like 50% sunlight throughout a solar day. Then you have maximum surface temperature, which maps maximum surface temperature throughout a whole entire Mercury solar day, sunrise to sunrise. And that permanently shadowed region stays pretty cold, you know, around 200 Kelvin, you know, maybe a little less, and it ramps up pretty quickly to go 400 and even 600 Kelvin on this side that faces the sun. And on top of that, stability depth models were made. And for this example, I'm showing coronine, which is a volatile organic compound. It's a polycyclic aromatic hydrocarbon. And it maps the depth in which these volatiles would be lost at a sublimation rate of 1 millimeter per billion years. So this is saying black, stable on the surface, blue, it is stable, you know, about 0.5 meters under the surface, and so on. And coronine is just one example of the many organic compounds thought to exist in Mercury's polar craters. Coronine is in no way special. So after we have all those models created, the first step is to examine the boundary of the deposits to see what we can find, see what matches up with what. And top left, this box shows like the general placement of this image inside the crater of Enzer. And here's a high resolution of Enzer's low reflecting surface at 38 meters per pixel. And it's important to note that this bottom left area is saturated part of the CCD. So this region is still part of Enzer's low reflectance polar deposit, but it's been compromised by the oversaturated pixels from the surrounding sunlit region. But moving on, when we plot the strictly permanently shadowed region from that model we saw before, we see that the low reflectance polar deposit extends outwards of up to like 500 meters beyond the permanently shadowed region, which is different from what was previously thought. And here on this third part are the maximum temperature boundaries that align best with the low reflecting surface. The 250 Kelvin maximum surface temperature line seems to fall slightly inward, whereas a 300 Kelvin is a pretty great match to the low reflectance polar deposit. And when you get out to the 350 Kelvin line, you see that it becomes kind of awry and starts to match that of the sunlit region, like for the top part and stuff like that. However, it's difficult to pinpoint an exact maximum surface temperature because of the lack of a distinct low reflectance boundary, especially for Enzer's northern part right here. You can't really tell exactly when that low reflectance deposit begins or ends. So for that reason, a range of maximum surface temperatures between 250 Kelvin and 350 Kelvin is concluded for Enzer's low reflectance polar deposit. The low reflectance deposit also aligns remarkably well with the surface stability boundary of cornine. But since the surface stability boundary for cornine is slightly smaller than that of the low reflectance polar deposit, as you can see like a little bit here, even though you can't really tell where exactly it ends in this part, we're led to believe that compounds with slightly less volatility than cornine can also exist within Enzer's low reflectance polar deposit. And it should be stated again that cornine is not special. It's just one proxy for all of the hydrocarbons and organic compounds that likely exist within these craters. And here's another example. We have laxness. This is the location of the image within the crater. So the permanently shadowed region falling at least 250 meters short of the low reflectance boundary, even though it's hard to tell where exactly the boundary ends for this part of the image. And plotting the 250 to 350 Kelvin lines, you see that they all match up fairly well, and there's a steep temperature gradient as you move away towards that permanently shadowed region of the crater. So again, it's hard to place an exact temperature, but it's definitely in the realm of 250 to 350 Kelvin. And we still see that cornine corresponds very well to the low reflectance polar deposit. And then one more example quickly is Fuller. And same thing, small permanently shadowed region, 250 to 350 temperature lines that match up extremely well, except for the 250 Kelvin line right here for Fuller is a great indication that 250 is on that lower limit of what we expect, because obviously this is that C cut is kind of that's not exactly what the low reflectance polar deposit is, so it has to be greater than 250 Kelvin. And we see that same with the cornine. So again, it's easy to conclude that slightly less volatile compounds than cornine also exists within Mercury's polar deposits. So this graph shows the sublimation rates of various volatiles that could exist in Mercury's polar craters. And for example, here you see water that doesn't have long-term stability at temperatures above 120 Kelvin. And as a general rule for most of these craters, or as for most of these compounds, as molecular mass increases, volatility decreases. But this research suggests that there are compounds that are stable to temperatures higher than this graph displays at 250 Kelvin. So one of those could be polycyclic aromatic hydrocarbons like cornine, which would fall somewhere around there on a graph like this, and that are stable up to 300 Kelvin and beyond, and are abundant enough in comets and meteorites and asteroids to produce a dark layer in Mercury's polar craters. So the next step was, instead of looking at the boundaries, was looking at the brightness variations within Mercury's volatile polar deposits. And simulated images were great at doing this. Simulated images, which modeled the direct sunlight onto the crater, as well as the scattered sunlight into the permanently shadowed region, use that digital elevation model topography to simulate a specific image at a specific time. And these simulations can help us understand if the brightness variations within these volatile deposits are physical or not, if they're on the surface or if they're just a cause of light scatter. So here, bottom left, this is a simulated image for Fuller. And the second image, these are outlines that outline the dark regions of the simulation. And then this third image is the real image of Fuller. And then when we take these outlines from the simulation and overlay them on top of the real image, we see how well they align with the real image. And that suggests that the brightness variations in the WAC image are the result of topography, not surface volatile compositional differences, because these simulated image assume uniform surface albedo. So, within the simulations, the brightness variations shouldn't be changing unless they're due to light scattering into the permanently shadowed region and then up into Messenger's camera. And another cool thing to point out is that here in the real image, you see a distinct low reflectance boundary, caused by those volatile organic compounds. And you don't see them at all. You don't see that at all in the simulated images, which is good because, since this is just assuming uniform surface albedo throughout the entire crater, then this confirms, with even more precision, that yes, this boundary right here is due to something physical happening on the surface. And it's not the cause of light scatter like the brightness variations are. And one more example of that is the prey. So right here we have simulated image, outline the bright regions of the simulated image, real image, place the overlay of the simulated image contour lines on top of the real image, and we see that the brightness variations agree very well with the simulated image and the real image. And this, again, suggests that the brightness variations are the result of topography. It's reflected sunlight off of the prey's topography. It's sufficient to explain the prey's pixel brightness variations, whereas before, people suggested that there was multiple volatiles on the surface of the prey. So there was a bright volatile right here, there's a dark volatile right here, but that's not necessary to explain the prey's pixel brightness variations as for any of these polar craters that we looked at. And again, we see that nice low reflectance deposit boundary right here in the real image and not in the simulated image. And that's great confirmation that this is due to physical albedo differences on the surface of the prey. So quick conclusions, jumping back to those fundamental questions, what are these volatiles and what are their characteristics? We see that the low reflectance polar deposits extend slightly beyond the permanently shadowed region and correspond to maximum surface temperatures of about 250 to 350 Kelvin. And this boundary also corresponds nicely to the surface ability of cornene, supporting that Mercury's low reflectance polar deposits are filled with comets and asteroids and micrometeoroids as previously expected. Thank you. Yeah, happy to take questions.
All right, that was awesome. And let's see, we have a few questions in the chat. So Michael Poston asks, what temperature was used as the stability temperature for cornene? Is that corresponding to 1 meter per billion years?
Yes, 1 millimeter per billion years.
Okay.
For that stability boundary.
And the temperature?
It's not based off of a temperature. It's based off of cornene itself. It's based off of its sublimation rates and a bunch of other numbers off how cornene responds. And I'm not the model guy. That's Matthew Siegler. But it's not just we don't just say cornene is a temp and related to a temperature. It's deeper than that. If that answers your question.
I'll have to talk to Matt. Okay.
Okay.
And Julie Mitchell has, I think, a related question. But how is the stability of carnine calculated under mercury polar conditions?
Yeah, so it's calculated using like the volatility of chlorine itself with sublimation rates. As far as a few other things that I'm blanking on right now, I'm writing a paper on this so I could bring up more details. But the guy to go to for that is Matthew Siegler, or I'm always happy to like email more about that when I have like the exacts.
All right, so we'll read the paper and we will get Matt on one of these telecoms. But this is really cool work, even if you weren't the modeling guy. I think especially the topography stuff I don't think I'd seen before when you presented this at APL. So I think that's really important and interesting. So let's see. So Ed has a comment. He says carnine is a great proxy for long-lived hydrocarbons. NIST data show it doesn't fragment at 70 eV electron impact energies. Instead, it forms +1, +2, and +3 ions, and it fluoresces blue under UV light. There are so many ways for this symmetric molecule to hide energy. That which is new to me. I learned something new today. So, and we have 2 more questions in the chat. Shyama asks, what is the source for carnine? Is it made in situ or does it have to be delivered?
Yeah, it's definitely going to be delivered. That's the notion as of right now. You know, it's not going to be there when mercury forms. It's just kind of like it's coming off of comets, asteroids, things with, you know, high abundances of volatiles. And of course, carnine is going to be relatively low, and you know, the overall like which volatiles a comet is bringing is going to be mostly water and stuff like that. But it seems like there's definitely enough carnine to build up over time, perhaps through like a bunch of micrometeoroids, or perhaps one giant comet impact. That's still kind of up to that's kind of like up to debate right now.
So, but could it be formed by radiation interacting with cometary deposits?
I'm not sure. I haven't looked into that. I've thought about that, but I don't know enough to say anything about that, about how it would form on Mercury's surface.
Cool. Yeah. And Michael says yes, carnine can be formed by radiation. So yeah. But interesting nonetheless. And Elizabeth Fisher asks, any plans to apply this analysis to bright areas in Mercury's PSRs?
Yes, that's next up on the to-do list. So we're finishing up this right now for the lower flex polar deposits, and I've just finished gathering the WAC images for the bright polar deposits that are even, you know, higher up, like right next to the North Pole. So like I'm gathering images for these, and then we're going to do similar things and see what we can find.
That's super exciting. Yeah, I haven't looked at the Mercury data in a while, but I remember I did kind of a related analysis on the lunar surface using these surface stability boundaries for surface water ice. And I seem to remember that on Mercury, there was a rather large uptick in albedo at about 100 K, which is that boundary.
Yeah, no, it's awesome to see the differences just between, you know, these craters and these. You know, it's noticeable just in the images by themselves without even implementing the models yet.
Yeah, that'll be fascinating.
Yeah.
All right. Do we have more questions for Colin?
I have a question. My hand is up. Can I ask it?
Yeah, sure.
Great. Follow up on the question about transport delivery from cometary volatiles then. Given that happens over time, what is the rate of deposition that has to occur? How thick must the deposit be for there not to be, from what I can see at least, any impacts that actually penetrated the dark layer into the presumably brighter subsurface?
Yeah, so the question is, how thick is that dark deposit layer?
Yeah, how thick would it have to be for it to be as uniform as it is without any bright albedo holes in it from impacts? Yes, that's the question.
Yeah, so the thought is that it's a few centimeters thick, and that's not based off of any research that I've done. But the thought is that it also insulates that water ice beneath it, so that water ice wouldn't be there unless there was a sufficient dark layer that was, you know, a few centimeters thick to do that. But I'm not sure on the exact numbers.
Are there no impacts that penetrate through that dark layer then? If it's only a few centimeters thick, there should be a lot of
There are actually.
Okay.
Yeah, that's yeah, there's a paper by Ariel that looks at that, and there's like little high reflectance circles within craters like Bechet and I think Enzer, and that's what those are thought to be. Is they're just little tiny, you know, baby craters that, you know, just spew up that high reflectance ejecta onto the surface above that dark deposit, which is really cool too, since we get to see that in action.
Any chance of using maybe the accumulation rate of this dark material then, and those impact craters to estimate crater rates, impact rates at the poles? Because we can, you know, it's kind of.
I don't see why that's not possible. You know, the time rates for all of these craters and the impact rates is still up in the air, but that definitely seems like a thing.
You might understand the, yeah, it'd be hard to understand what what would be the cometary input rate. You're going to be guessing at one, you derive another rate, so maybe not. But still, nice work. Thank you.
Thank you.
Great, and I see Ariel has her hand up.
Hi, Colin. This was really great. I had a quick follow-up question about your intention to look at some of the bright ice at the higher latitudes. I was just curious kind of how the resolution of the images would affect your topography model if they're not part of the low altitude campaign.
Yeah, so I've already seen with the WAC images that the resolution isn't quite as good. You know, I'm like averaging around 90 to like 100 meters per pixel for that like high northern region. And that's going to show in the MLA data as well, right? Because it's going to be way less dense up there. So as of right now, I think Erwan still plans to make 125 meters per pixel topography models. But if that seems to be a stretch, they might have to bump it down just based off of the sparseness of data up there. But we're just beginning that, so I'm not exactly sure what road we're going to go with the model and image resolutions.
Cool, thanks. Looking forward to it.
Yeah, thank you.
We have time for a few more questions, if folks have them. All right, I have one. So Colin, I'm just looking at the slide you have up now. So it looks like the low altitude images are available at a range of different longitudes. And so I was wondering, do you see any difference in the extent of that dark albedo boundary for things that are like at the hot pole versus the cold pole? Or basically, do you see any longitudinal trends on the extent of that dark albedo boundary?
No, I haven't. I mean, just to be, I haven't really looked at any longitudinal trends. You know, simply we're kind of basing everything up into like latitudinal chunks, right? But I don't see why the dark deposits would follow any type of longitudinal trend. You know, they're all going to be relatively the same temperature. Mercury's, you know, has no like tilt or anything like that, so there's no like seasonal changes. So I feel like the temperature variations should be the same.
Yeah, like I know that I forget which longitudes are the hot poles and which are the cold poles, but the hot pole longitudes, they're always at noon near perihelion. So even though there's no tilt, when they get hot, they get really hot, and cold poles, when they get cold, they get really cold. But yeah, but I'm not sure off the top of my head what you might expect either. So, but yeah,
actually,
it was just a thought looking at.
Yeah, we do have two more craters up above where we can't see, you know, up like all the way up here. So maybe it is worth looking at that, because I haven't thought about that at all, about how it varies with the perihelion and things like that.
And some of Nancy's earlier work actually showed this, Pravarthi. So where Colin is looking closest to the pole, you don't tend to see those longitudinal differences, but the farther you extend from the pole where those variations and the hot and cold poles or stronger, you do see a distribution of the ice that correlates to that thermal difference.
Cool,
That's
thanks, Ariel.
like 65 to maybe 75 degrees. But yeah, definitely.
Okay.
Good
Cool.
to know. And we have time for maybe one last quick question, if anyone has one. All right, if not, then thanks again, Colin and Rosemary, for a couple of great presentations. And we have 3 minutes until 3. Does anyone have any final thoughts or comments? All right, if not, well, let's see. So in other news, hopefully everyone got my email yesterday in which I attached a draft of a potential lunar volatiles related white paper. So if you get a chance to look at that, take a look. It could definitely use more input. And I will probably be reaching out to some of you individually over the next couple of weeks to get your input on that. And on a related note, there's also a League Survey joint meeting on Wednesday. I think that is from 12 to 4:30 p.m. on May 20th, Wednesday, which is also going to focus on discussing potential white papers. Does anyone know anything else of interest that might be coming up, or anything interesting you've seen lately?
I guess I'll just follow up on that quickly. This is Ariel again. But Nancy Chabot and I are also leading a white paper on Mercury's ice deposits. So if you're interested in what Colin talked about and some of the themes that we discuss, and you haven't received an email from us, then please definitely email me and I can be sure to distribute that to you as well.
Yeah, thanks, Ariel. And if anyone else is getting started or planning to work on white papers, feel free to use the Friends of Lunar Volatiles list to send those around or look for co-authors and so on. Otherwise, we are almost at 3 p.m. So if there's nothing else, we'll call it a day for today. Thank you again for dialing in and for all your great presentations. And we will meet again about a month from now. Thanks, everyone.
Cool. Thank you, Parvati.
Bye.
Bye.
Thank you.
Bye.